In a previous video, we talked about how we can take a vector. We could take, all kinds of things and break it down into its horizontal and vertical components. And we saw how it made things very easy for adding vectors together, because you could just put the horizontal components in one column, put the vertical components in another column, add those guys together, and you can find the net result, right? But there's another way that we can do this. So the way that we talked about it before is that we would just take a vector and we say, okay, here's the x component, here's the y component, and we were done with it. But sometimes we want to compare that to another vector. We want to see, what part of this vector is going to be parallel to a second vector, and what part of the vector would be orthogonal or perpendicular to it. So here is something we're going to be doing. We're going to be taking a vector v. I gotta get the right color here. There we go. We're going to take vector v, and we want to see its vector projection. Let's see the vector projection of v onto a second vector w. So we're going to break this down into two parts. One part that is going to be parallel to vector w, and another part that's going to be perpendicular. Okay, so this vector projection of v onto w, we're going to call this guy v1. And really what we mean by it is this. So suppose you have, here is your vector v, but then here is some vector w. We want to be able to break down and see this vector v, where part of it is going to be parallel to this, and the other part is going to be perpendicular to this. So how do we do that to figure out what those component pieces are going to be? Because we want it to be, again, parallel to w. All right, so here is what we're going to do. Here's the formula for this. So the way we find vector 1 is by working out this expression. We'll do v dot w over the magnitude of w squared, and then times vector w itself. The thing to understand here is that all of this is just a number. It's not a vector at all. It's going to become some kind of scalar that we're going to multiply times w to get. And then to find, okay, so we're saying that this is going to be our v1. v2 is going to be the piece that is perpendicular to it. And the way that we find v2 is just to take vector v and subtract off v1. Nothing really too crazy about that, because we know that we can break v down into a multitude of components. And so if we know what one of those components is, we just subtract it, pull it out, and we'd be left over with that vertical part. All right, so, excuse me for the paper, let's find the vector projection of v is equal to 2i plus 6j on to vector w, which is 2i plus j. Okay? So let's look at the formula that we have above. We want to find the first part. So let's find vector v1. And we'll do that by doing v dot w over the magnitude of w squared, and then that's going to be the scalar multiple times vector w. All right, so again, I want to kind of make things nice and clean. So off to the side, I'm going to work these guys out. So let's find v dot w So that's going to be 2 times 2 plus 6 times 1. So 4 plus 6 is equal to 10. All right, so the numerator is just 10. And then we want to find the magnitude of w squared. Well, that is essentially you doing the square root squared, so it's just going to be the two pieces inside here. So that's going to be 2 squared plus 1 squared. So that's going to be 4 plus 1 is 5. Square root of 5 squared, and that's just 5. So this is all divided by 5 times vector w. So cleaning that up, that's 2 times vector w, which is 2 times 2I plus j. So v1 is going to be 4I plus 2j. So when you compare this to vector w, since v1 is really just a scalar times w, it means that v1 is parallel to w. So that means that they are going in the same direction. Different magnitude, that's fine, but they're going in the same direction. That's what's important. So then whatever's going to be left over is going to be the piece that is perpendicular to w. So this is going to be v minus v1. All right, so v is 2I plus 6j minus 4I plus 2j. So if we look at this and we distribute that negative, 2 minus 4 is going to give me negative 2I. 6 minus 2 is going to give me plus 4j. And just a quick thing here, you can see that if I were to add v1 and v2, that gives me the 2I plus 6j, right? And if you were to compare these guys, you would find out that v1 and v2 are orthogonal. So if you went further and you did v1 dot v2, you get 0. They are orthogonal. One part is parallel to this vector that we're trying to project onto. The other part's going to be perpendicular to it. So it's kind of a nice way sometimes of rewriting our vector in comparison to another already established vector. All right, so what we're going to do is we're going to, in the next video, do a couple of examples, like real-world examples, and do these vector projections and see how they play out. So stick around for that.